Hello everyone, welcome to this today's session Holzer method, which is part of the course ME22088. I am Dr. C. Sendamaraikanan, Associate Professor in the Department of Mechanical Engineering at SVC. Now, let's delve into the specifics of Holzer method. As you can see, it is fundamentally a trial and error approach used to determine the natural frequencies of a system. The core idea is to assume a trial frequency and then work through the system. A valid solution is found when the assumed frequency satisfies the system constraints. It is important to note that this method typically requires several trials to converge to the exact natural frequencies. However, a significant advantage of Holzer method is that it not only helps us to find frequencies but also provides the corresponding mode shapes. Now consider how the Holzer method can be applied to torsional systems. Here we seeing an example of an undamped torsional semi-definite system. I want to recall what is semi-definite system. A semi-definite system is the one where any one of the natural frequency should be 0. So with that recall, I am continuing this chapter. Here the shaft holding 3 discs, which is labeled as J1, J2, J3, that is the polar moment of inertia, connected by shaft having a torsional stiffness of K1, K2. If there is a twist, the angular displacement of this disc are denoted by theta 1 for J1, theta 2 for J2, theta 3 for J3 respectively. For this shaft with having 3 discs, the equation of motion can be derived using same Newton's law. We already seen in the first unit as well as in the second unit how to derive the equation of motion when there is a force acting on a system. So just I am recalling it. So there should to be a inertia torque and it is going to be opposing torque. What is inertia torque? Inertia torque is nothing but polar moment of inertia multiplied by the angular displacement. So this is the inertia torque, which is to be equivalent opposite to the stiffness of the system. Stiffness in terms of stiffness force. So stiffness force in sense force equal to stiffness into the displacement. Here it is angular displacement. So angular displacement means here the stiffness K1 is going to be equally responsible for J1 as well as J2. So whenever there is a twist, what will happen? The theta 1, theta 2 both will have a angular displacement. So the difference in this will be taken into account to calculate the displacement to calculate the stiffness force. So here the difference in displacement, angular displacement is theta 2 minus theta 1 into kt1. This will give you resisting torque. Okay, so this is the applied torque. So since it is equal and opposite means when we take everything in along the one side, you will get J1 theta 1 double dot plus kt1 into theta 2 minus theta 1 equal to 0. The same fashion, if supposed to write equation of motion for J2, then what will happen? For the J2, the inertia torque is J2 theta 2 double dot. It is simple, but in case of stiffness force, the stiffness force is due to because of kt1 as well as kt2 we have to account when it is going to be for the theta 2. So for that purpose, if it is kt1 stiffness force means kt1 into theta 2 minus theta 1. So that is one stiffness force. Then the same J2 is connected with kt2 also. So stiffness force due to kt2 is stiffness kt2 multiplied by difference of angular displacements, that is theta 2 minus theta 3. So if we put all things, that is resisting force as well as applied force on a left hand side, then we will get it is the equation is equal to 0. The same way we are getting the third equation for the third disk, that is inertia torque is J3 theta 3 double dot, that is theta 3 double dot means it is acceleration torque, plus the J3 disk is connected with stiffness kt2. The stiffness force is kt2 into theta 3 minus theta 2 equal to 0. So this is the three simultaneous equation of motion for the disk which is given here. So the next we will see how to identify the natural frequency using the Holzer method. Continuing our analysis of the same torsional system, we are going to consider an assumption, that is here we are assuming that Vi equal to theta 1 cos omega t plus pi. This is the assumed displacement. If we are going to substitute the same thing in the previous equation of motions, then what will happen? We will further differentiate this one with respect to first t1, then we will get velocity, then 2 times we will differentiate, we will get the acceleration. Then that we can write that omega square j1 theta 1 equal to k theta 1 minus theta 2. The similar way second equation and third equations and all written. So by summing all this equation we can able to see that is omega square j1 theta 1 will definitely equal to 0. That you can see it here, kt1 theta 1 is positive here. Then kt1 theta 1 will also be somewhere negative. Similarly kt1 theta 2 is positive here and kt1 theta 2 somewhere will be negative. So like that everything will get cancelled out. That's why the summation of omega square j1 theta 1 will be equal to 0. This states that sum of the inertia torque of the system must be 0. Trial frequency must satisfy this requirement. So how do we actually implement this trial and error method? In the Holzer method for torsional systems, we start by arbitrarily assuming the amplitude of the angular displacement of the first disk, that is theta 1, to be equal to 1. Then equations what we have it in the second slide, we can able to calculate the amplitude of the subsequent disk. It is nothing but take those equations, substitute theta 1 equal to 1, that's all. Then you will eventually get this theta 2 term and theta 3 term. So based upon our initial assumption, the assumed angular frequency omega, the moment of inertia and torsional stiffness, we are going to be see that this values, if I am substituting theta 1, theta 2, theta 3 into this equation, we have to see that whether it is the constraints are satisfied or not. Okay, so once we have this value, we have to substitute them in this equation and we have to check if this sum is equal to 0. If it is, then our assumed omega frequency is natural frequency of the system. If the sum is not 0, it means our initial guess for omega was incorrect. So we need to repeat the process, entire process, with a new trial value for the frequency. This iterative procedure continues until we find a frequency that satisfies the condition. So I am concluding in this slide that This is the generalized formula to, we have to see that our considered natural frequency should to be substituted and it is to be satisfied. If it is not satisfied, we have to go for trial, and it will be iteration till we are getting that correct value of omega should to be match and it should satisfy this equation. Here this graph illustrates how we can plot the natural frequency of the torsional system using our Holzer method. On the vertical axis we have the torque M on the which is going to be applied at the last disk in our 3-disk system. So MT equal to MT3. This torque is plotted against the chosen angular frequency on the horizontal axis. As we discussed earlier, a natural frequency is achieved when the sum of the inertia torque is 0. This condition corresponds to the point where the torque at the last disk becomes 0. Therefore, natural frequencies of the system are the values of omega at which the curve intersects the horizontal axis. So wherever the curve intersects, that value should be taken as our one of the natural frequency. So in this example, we see such 3 natural frequencies. That is, first omega is 0, second omega 2 is 707.5 Hz, third omega 3 is 1122.4.7 Hz. Further, the amplitude of the angular displacements we calculated for each disk at this specific natural frequencies represents the mode shape of the system, giving us insights how the system vibrates at each of the natural frequencies. Let's solidify our understanding with respect to the Holzer method by considering another practical example. Consider the arrangement of a compressor, a turbine and a generator which is available in a thermal plant as shown in the diagram. We are having that moment of inertia for each component, that is compressor is given as 8 kg meter square, turbine is given as 6 kg meter square, generator is given as 4 kg meter square. And as the same way, they are also given that shaft that is having a torsional stiffness K1 is 4 meganewton meter radians between the compressor and turbine, and it is 2 meganewton per radians between the turbine and the generator. So our task is to use the Holzer method to determine the natural frequencies and the corresponding mode shapes of this torsional system. This table demonstrates the step-by-step application of Holzer method to our thermal power plant example. As you can see, we have organized the calculation by station wise. The station 1 represents compressor, station 2 represents turbine, station 3 represents generator. Table shows the parameters of each component, namely their moment of inertia as well as the stiffness component. We are going trial basis. In each trial, we start by assuming a specific value for the angular frequency. You can see these assumed values listed below the trial numbers. For example, in trial 1, the omega 1 is 0. Trial 2, it is 10. Trial 3, it is 20, and so on. Corresponding to each assumed omega, we also calculate omega square, which is shown in the second row. That is, 10 means 10 square is 100, 20 means 20 square is 400. For each of these assumed frequencies, we then go through the sequence of calculations for each station. We start with an assumed angular displacement for the compressor, that is theta 1 equal to 1. Then we calculate the inertia torque, that is omega square J1 theta 1. Since omega is 0, here this will become 0. Using the torque and stiffness, next thing we have to go for the next trial. We are substituting omega equal to omega square is 100, J1 is given, theta is now 1. So we are getting 800. So we are continuing the same. Next 3, then 71 trial, we are substituting that omega square equal to this value and getting that J1 is same, KT is same. We are getting that MT is 0.392E7. By comparing this final two values across the different trial with different assumed frequencies, we can identify the natural frequencies as those trial frequencies for which the value of M3 is very close to 0. That is our main important task. So you can observe in the table how the value of M3 changes as we try different values of omega. For instance, in trial 71 and 72, where we assume the frequencies are 700 and 710 radians per second respectively, final torque what we get at the station 3 is, that is the M3 is 0.119 E6 and minus 0.494 E5. We suggest that the natural frequency lies between 700 and 710 radians per second. That means if I draw the graph, we have to consider the graph also. So initially the positive value is coming into picture, that is 0.1119 e power 6. Then the next negative value is coming into picture. So the plot, if we plot, it will cross like this. So this value at this point we are getting the natural frequency. So 0.119 is arrived at, it is for 71st trial, that is 700 natural frequency. This negative value is at 710 radians per second. So one positive value, one negative value. So definitely the curve has to cross the 0 value. So this one we have to take it as the, we have to plot the graph. From the graph we have to take this value. That is our natural frequency, exact natural frequency. So we are continuing the previous slide. That is, in this slide, here I am summarizing the first two flexible mode shapes obtained from the Holzer method. Recall that the torque to the right of the generator, that is M3, that is calculated at last, should to be 0 at the natural frequencies. By performing several trials, we closely spaced values of omega in the vicinity where M3 is going to be approach 0. We accurately determine the natural frequency and the corresponding mode shape. The first flexible mode is shown with the natural frequency of omega 2, that is 707 radians per second. The relative amplitude of the angular displacement for the compressor, turbine and generator in this mode is approximately 1, 0 and 0.001 respectively. This indicates that in the first mode, the compressor and generator, compressor is having one value, generator is having one value. Both are vibrating in opposite direction, with the turbine acting as a sort of pivoting point with very little displacement. The second flexible mode, which is going to be having, we have to see this line. So in this line, it is going to be 1224.7 radians per second. Here the relative amplitudes are approximately 1, -1, -2. Okay. So this shows that all three components are vibrating, but with different amplitudes and relative phase. The generator has the largest amplitude of vibration, followed by turbine vibrating in the opposite direction, and then the compressor also vibrating in the opposite direction to the turbine, but with a smaller amplitude. These mode shapes are crucial for understanding how the system will perform, or it is vibrating at its natural frequencies, and it is helping us to design the system such a way we can avoid the resonance. It is important to note that the Holzer method isn't limited to just torsional systems. It can also be effectively used for vibration analysis of spring mass systems. Here we are having a diagram with multiple masses M1, M2, M3 until Mn. Similarly, stiffness values ranging from K1, K2, K3 until Kn-1. Similar to the torsional system, we can derive the equation of motion for each mass. That is, for first mass, according to Newton's law, m1 x1 double dot mass into acceleration equal to stiffness force, stiffness into difference in displacement, because k is connected with both mass m1 and m2. So x1 minus x2 will come into picture. So in this fashion, we are also writing the second equation m2 x2 double dot plus k1 x2 minus x1 plus k2 x2 minus x3 equal to 0. To solve this, what we will do, we are assuming a harmonic motion such a way that x of t equal to capital X I cos omega t, where capital X suffix I is the amplitude of the mass m with suffix I. That means mass m1 means here x will be x1, here m will be m1. If it is mass 5 means x5, m5. So as you can see, the form of this equation is quite similar to what we encounter with the torsional system, involving the square of the frequency, that is omega square. How it is coming? Once again, we have to substitute what is going to be. Here we are differentiating x of t, we will get x dot cos omega t. If we are differentiating with respect to time, it will change as sin omega t into omega. Once again, if we are differentiating, we will get x sin omega t will be differentiated to become as cos omega t, and omega square will come into picture. So that one we are substituting here. We are getting x1 dot, that is acceleration value is omega square x1 into m1 equal to k1 x1 minus x2. In a similar way, we are substituting this. Instead of x2 acceleration, we are substituting omega square of x2. Hence, now this is analogous to our same torsional system equations. Here the mass is analogous to moment of inertia. Displacement amplitudes are analogous to angular displacement amplitudes, as well as the stiffness of the spring is analogous to, there it is, torsional stiffness. This similarity allows us to apply the same trial and error method approach, that is our Holzer method approach, to find the natural frequencies and mode shapes of spring mass systems as well. So similar to the torsional systems, for a spring mass system, we start by assuming the amplitude of the first mass displacement is equal to 1. Then we can use the recursive formulas to calculate the displacement amplitudes x2, x3 and so on up to the last mass. These formulas depend on the assumed angular frequency omega, the given mass and stiffness of the springs. After calculating the displacement amplitude of the last mass, that is x suffix n, we can determine the resultant force acting on it. In a free vibration scenario, this force must be 0 at a natural frequency. Therefore, to find the natural frequencies of the spring mass system, using the Holzer method, we would repeat this process for several trial frequencies and then plot a graph of the resultant force on the last mass against the assumed frequency omega. The natural frequency of the system will be the values of omega at which this force F becomes 0. So whatever I told now, it is nothing but we are drawing a graph against force versus omega. So we are plotting it as in the same similar fashion of the torsional system. So wherever this curve is crossing the 0, that value will be our natural frequency. This will be always is going to be omega 1, this is omega 2, this is omega 3. This value is omega 3. Thank you for your time and attention. So in this video lecture, we explored Holzer method, a powerful trial and error technique used to determine the natural frequencies and mode shapes of vibrating systems. We begin by understanding the application of the Holzer method to torsional systems, examining how to set up the problem, assumed trial frequencies, and iteratively calculate the system's response to find the frequencies that satisfy the boundary condition. Then we looked at an example of a torsional system in a thermal power plant, demonstrating the step-by-step calculation involved in the Holzer method and to interpret the resulting natural frequency and mode shapes by plotting the graph. Finally, I briefed you about how to adapt the Holzer method to the spring mass systems. I hope this lecture has provided you with a clear understanding of the Holzer method and its application in vibration analysis. Thank you.